Hello and welcome to another video lesson with Takoa Lawson. Today we're going to start the AP Physics 1 unit circular motion. Before getting into the unit, let's talk a little bit about the big ideas that College Board has put out that relate to this topic. There's 4 of them, starting with big idea 1, that objects and systems have properties such as mass and charge. Systems may have internal structures. Really, it's going to be about the mass idea here. We're going to talk about how to find inertial mass, and then in the next topic, universal law of gravitation, we'll talk about finding the gravitational mass and comparing the two, which it turns out that they're identical, regardless of which way you measure it. And then this idea that systems have internal structures. When we talk about a body versus a system, or an object versus a system, object might have internal structure, but we ignore it. While a system is multiple objects that we are not ignoring the structures or that they relate or interact with each other. So the idea that different things can actually have interactions. Big idea number 2 is going to be about fields existing in space that can be used to explain a lot of those interactions. There's 2 fields that we're going to really look at. One's going to be gravitational field, which will be the main focus of AP Physics 1. And then towards the end, we'll talk a little bit about electric fields, although electric fields and magnetic fields would be looked at much more in AP Physics 2. Big idea 3 is about the interactions of objects with other objects being described using forces. Really, it's that when one object applies a force to another object, it receives the same force back. It's Newton's third law of reciprocal forces. So it's just this idea that forces exist in pairs. No object can apply a force to itself. Any force that exists is because of an interaction with some other object, even if we're not considering the object as part of the system. The force can only be caused by another object. The last big idea 4, is about interactions between systems can result in changes in those systems. It's really that the forces that an object experiences from another can end up causing it to accelerate, can end up causing it to change direction, can end up causing some kind of change to that system. So it's really that these forces of interaction actually can be more than just a force that exists. They can be a force that causes change within the system. In uniform circular motion, the reason it's called uniform circular motion is that the speed is constant. So this is an object that's following a curve or going around a circle. It may only be going around a portion of a circle. It doesn't have to complete a full circle to be circular motion. Even an arc would be considered circular motion. One of the things that will be helpful to describe circular motion, both uniform and non-uniform, but starting with uniform, is the idea of a circle and understanding the parts of a circle. So on the right here, you can see this diagram shows us a circle. It shows a couple of important characteristics of a circle. One is the radius. We'll use the radius to refer to as the radius of curvature. So when you're taking a turn around a road, when you're following a loop on a track, when you're going through a circular motion, that circular path will have some kind of curvature, and there's some radius to that curvature. All of our curves are going to be uniform curves in the idea that they would be a smooth arc on a circle. We might have multiple arcs connected to each other, so we could have a more sharp turn and then a less sharp turn afterwards, and they'd each have their own radius of curvature, but the radius of curvature of each part would be constant. If you were to travel around from point A, following the entire circle and returning back to point A, then you would travel the circumference of the circle, which will be important if we're talking about an object traveling around a complete loop or multiple complete loops. Or if we know that you did half a loop or a quarter loop or some specific portion or percentage of the loop, we want to be able to get the circumference. And so the circumference, as we all know, is defined by 2 pi r, where r is the radius, or since 2 times r is the diameter, we could say pi d, or pi times the diameter. If you're only moving a segment or a portion of the circle, for instance going from point A to point B on this diagram, then you would carve out an arc. A certain distance we'll refer to as delta S. That will be the distance between A and B on that circle. We can determine that a couple of ways. One, we can multiply that angle that's swept out by the 2 radial lines extending from the center of the circle to A and the center of the circle to B. That angle theta in radians times the radius in meters would give me that arc length in meters, times the radius in centimeters would give me that arc length in centimeters. So we can also determine that by taking the speed of the object. You'll notice here we identified the speed as the magnitude of the velocity, and it's really important because velocity is a vector and includes direction. Speed is just the amount of the velocity without consideration of direction. So we take the speed and we multiply it by the time that we're traveling. And so speed times time. When the speed is constant, you're not speeding up or slowing down, there's no acceleration. gives you that distance, that arc length that you travel. It goes back to our change in position is equal to v naught t plus 1/2 at squared. Since a is 0, turns out its change in position is equal to v times t. There are a couple of concepts that are important. We've already talked about one of them, which is circumference, or a portion of the circumference, some kind of arc. Another one is the idea of a period. A period is the time that it would take to complete one loop. So if you start at point A and return back to point A, the time it takes to make that entire trip would be one period, or the time of a period. There's another relationship. We could talk about the rotational frequency, or we could talk about the frequency of traveling around the circle. Now, frequency and period are not the same thing, but they are reciprocals of each other. So if you know the period, you know the frequency. If you know the frequency, you know the period, which means that if it takes 4 seconds to travel around the circle once, then the period's 4 seconds. That means the frequency is 1 divided by 4 seconds, or 1/4 of a hertz, 1/4 of a reciprocal second. We'll work more on the idea of hertz and frequency later on in the year, but it could come up in a couple of problems. If we wanted to find the speed of this object as it's traveling around the circle, we can do that a couple of different ways. One is if we are told it's traveling at 4 meters per second, then we know the speed's 4 meters per second. Another is they might tell us the period that it takes. Like I said before, if it takes 4 seconds to travel around the circle once, then the period of 4 seconds, then we simply need to be able to figure out how far it traveled around the circle, which, as was mentioned in the other slide, was the circumference. We can take the circumference and divide it by the time in a period to get the speed or magnitude of the velocity. We can substitute in 2 pi r for the circumference, or pi d if you prefer, using the diameter, and divide that by the period, and that would also give us the speed. It's the exact same relationship. Or if we have a segment, the arc length, delta s, we can divide that segment traveled by the time it took to travel that segment, or delta s divided by delta t. And of course, as mentioned in the previous slide, since you can get delta s using the angle swept out in radians, and make sure it's in radians. If it's in degrees, you'll get the wrong answer. The radians times r times the radius. If you know the angle in radians and you multiply that by the radius and divide that by the time it takes to sweep out that arc length or to travel that arc length, you can also get the speed. Why this is important is in uniform circular motion, speed is constant. So one of the common things that we're trying to figure out is how fast you're going. Or if you're going a certain speed, how long does it take you to complete a circle? What's the period? Or how far will you go in a certain amount of time? What's the arc length? Or what time does it take to travel a certain arc length if you know the speed? So all of those are different relationships that we can be asked about. You'll notice in the diagram, the velocity is tangent to the circle at every point. So by definition, it's perpendicular to the radius. What that means is that anywhere along the circle, as you can see here on point A, we're tangent to the curve, and you can tell that this object is traveling around the circle in the counterclockwise direction. The speed is constant. We're not speeding up or slowing down, but the velocity is changing direction constantly. So as you can see, when we compare points A and point B, we have the same speed, we have the same magnitude of velocity, but we're not pointing in the same direction. In fact, no 2 points anywhere on the circle would have the same direction. So the velocity is constantly changing in some way. The speed at point A is equal to the speed at point B, but the velocity at point A is not equal to the velocity at point B. They're equal in magnitude, but not equal in direction. So a changing velocity, by definition, means there's some kind of acceleration. The question is, how do we describe this type of change in velocity or acceleration, since we can't use our normal linear descriptor? So we've been able to describe acceleration or changes in velocity when it was increasing or decreasing in magnitude. We did that a whole bunch in one-dimensional, two-dimensional motion. Yes, this is a form of two-dimensional motion, but this is unique. In this case, unlike our other examples, we're not speeding up or slowing down. We're simply changing direction. So we need some way of being able to define what's happening. There's a little animation here that will try and help emphasize that point. So we're going to take A, we're going to translate that, move it up to point B. You can see the vector A is the exact same length. It's just been moved to point B, so we can compare that. See, vector A and vector B have the same magnitude, but they do not point in the same direction. Well, if you go back to point A and you imagine moving 1 degree up, you would now, tangent line would be 1 degree rotated. And so if you went 90 degrees from that point, your tangent line would now be 90 degrees. And so what we find is that the angle theta that's swept out between the 2 points from the center of the circle or along the radius is actually equal to the angle theta between the 2 velocity vectors that were tangent. It's a rule mathematically, but hopefully you can see that as you move around the circle, as you sweep out an angle theta, that ends up being the difference between the tangent lines for the 2 different points. This will be important because we're now going to compare these 2 similar relationships. Even though they're not the same, they are similar. So on the right, you'll see the diagram that represents the piece cut out from the circle, where we have the radius that creates the 2 sides, the angle theta, and then delta s, or the arc length between the points A and B. Then on the left, you see we have vector A, which was translated, and we have vector B, and we have the angle theta between them. If acceleration is the change in velocity over time, what we're trying to do is find a way of describing this change in velocity. Well, velocity is a vector, and we have vector A and B, and anytime we want to get the change in a vector, we simply subtract the final from the initial. Or, as you see over here, the final plus the negative of the initial, right? VB plus negative VA is actually VB minus VA. So what we've done on our diagram, if we've taken VA, because the negative of VA is simply a flipping of that vector, it's pointing in the opposite direction, and we've redrawn it tail to tip. So we have the first tail for VB, then we have the second tail, the tail of negative VA. We've drawn them tail to tip over here, so VB to negative VA, and now, or the difference between VA and VB is shown by this vector here. And what we have is a triangle that has 2 equal sides, an angle theta, and then the difference between them. You'll notice on this triangle, the one that's the wedge cut out of the circle, it also has 2 equal sides, but these are both r, the angle theta, which happens to be the same as the angle theta between these 2 vectors A and B, and then the wedge, or the arc length, between them. Now, it's true, these are very similar triangles. In fact, similar triangles, the ratio of the sides are equal to each other. But a smart student will notice that this is a little bit of a curve. So what we do is we describe this as theta decreases, or as time gets smaller and smaller. As time goes to 0, this angle gets smaller and smaller, and this arc length becomes more and more like a straight line. And in fact, you can imagine at this point where we had a very either large radius and small angle, that the curve would be so small that it would actually, in fact, appear to be a straight line. For those of you in pre-calc or in calculus, you know this is as, we could describe this in terms of limits, but we're not going to go there. We're simply going to say that this triangle and this triangle, as t goes to 0, where theta goes to 0, is similar, or are similar triangles, which means the ratios of 2 sides will be equal to each other. The ratio of 2 sides, in this case, we want to get theta. So the theta for here is going to be equal to the ratio of the change in velocity, or delta VAB, over either of these, right? And it doesn't matter whether we choose VB or VA because they are equal. Since we're not speeding up or slowing down, the magnitude of velocity B and the magnitude of velocity A is the same. They're just in different directions. So what we're really saying is that the change in V divided by V is equal to that same side over here, which would be V times delta T, divided by a side, which would be R. So we see that delta V over V equals V times delta T divided by R. What we're really saying is the ratio of this side to either side of this triangle is equal to the ratio of this side to either side of that triangle, because they have similar relationships, similar ratios. They have the same angle theta, and they have 2 equal sides. So they have to be similar triangles. Now when you look at this, you might not instantly see that there's acceleration there. It's not obvious because what we have to first do is get delta V divided by delta T. So we're going to have to do a little bit of manipulation. We're going to multiply both sides by V. And then what we see is that delta V is equal to V squared times delta T divided by R. Now, delta V is your change of velocity, not your acceleration. But your change of velocity over time is your acceleration. Oh, notice there's a time factor there. So if we multiply both sides by the inverse of time, could have done that in one step, but just to show where it's coming from, we get that the change in velocity over the change in time is equal to v squared over r. Or that we can describe this type of acceleration, this change in direction of the velocity, as v squared over r. And we're going to refer to that type of acceleration as centripetal acceleration. Not to be confused with the linear acceleration that we've seen, where you're speeding up or slowing down, but an acceleration that doesn't cause you to speed up or slow down, causes you to change direction. Acceleration that's perpendicular to your motion. So there is no component making you go faster or slower. Since it's perpendicular to the motion, it simply makes you curve in that direction. And the centripetal acceleration, since it makes you curve in that direction, will always be pointed towards the center of the circle. It always goes along the center of the circle. That's true for anywhere on this circle because we're going into constant speed. So once we know the speed and we know the radius of the circle, we can get the centripetal acceleration. Like usual, now that we have a relationship between three different variables, be prepared to be asked if one variable increases or decreases, another one's kept constant, how will the third be affected, or what would going around a curve that is a smaller radius at the same speed versus a larger radius at the same speed mean in terms of the centripetal acceleration. Most problems that you'll run into will be uniform circular motion. The majority of them will involve an object traveling at a constant speed. But that's not the only type of circular motion. We could have something that's speeding up or slowing down at different parts of the turn. In that case, it's non-uniform circular motion because your velocity is actually going to be not only changing direction, but it's also going to be increasing or decreasing in magnitude. So this is traveling around a circular path where the speed is no longer constant. We see here a diagram that shows the point A and point B, but now not only do we have our centripetal acceleration, the one that's causing the velocity to change direction, we also have a tangential acceleration. And in this case, we can see at point A, our object is moving in the counterclockwise direction, and the tangential acceleration is also in the counterclockwise direction. And since the acceleration is the same direction as velocity, that means we're going to speed up. So when we look at point B, not only is our vector changed direction, it is also increased in magnitude because we're going faster. In this case, because our acceleration is in the same direction of motion, you're speeding up, but if our acceleration was in the opposite direction of motion, it would be slowing down. So it doesn't have to always be speeding up. A couple of things to remember. So we could talk about going around the circumference and the period. The problem is if we're speeding up or slowing down, that's no longer the speed that we're traveling at. That would be the average speed. So if we know the period and we know the radius, we can find the average speed by doing the circumference divided by the period. If we started from 0, then we'd know the average speed equals the final plus the initial divided by 2. If initial was 0, then we know that the final speed is exactly double the average. So only when it starts from 0 can we use that trick. If it doesn't start from 0, if we know what it started at, let's say that we knew that it started at 2 meters per second, and we knew the period and the circumference, then we could put that into V average equals V final plus V initial divided by 2 and solve for the final. Or if we know the final, we could solve for the initial. So we'll talk a little bit more about those functions and those relationships later on. But the average velocity is what we get if we took the circumference and divided by the period. We can get the instantaneous speed, or we can get the instantaneous magnitude of velocity using kinematics equations, or if we know the centripetal acceleration at that point. So if we know the instantaneous centripetal acceleration, since that's v squared over r, and we know the radius, we can actually get the instantaneous speed at that point. But it's important to be careful, because the centripetal acceleration is constantly changing if you're speeding up or slowing down, because it's based on your speed. So if you're going faster at some point later, then you're not going to have the same centripetal acceleration as you did when you were going slower. So just be aware of that. When we talk about this tangential acceleration, and we're interested in figuring out what it is, that's back to what we've been doing. That's pretty much kinematics and doing the linear kinematics, which we looked at before. So the easiest way is if we know the final velocity b, we know the initial velocity a, we can simply find the difference between them, or the change of velocity, divide that by the time, and that's the linear or tangential acceleration. We could use some of the other kinematics equations if we have different information, for instance, the arc length and the time, or the arc length and the final and initial velocity. However, the one thing that hasn't changed is the centripetal acceleration. It's always v squared over r. Whether it's uniform or non-uniform doesn't really matter. but the big difference here is that unlike uniform, where the centripetal acceleration is constant, in non-uniform, the centripetal acceleration is instantaneous. It depends on where you are. So you have to know the instantaneous speed or velocity, since the radius is constant, to find the centripetal acceleration. When we want to figure out the total linear acceleration of this object, since it's experiencing a centripetal acceleration towards the center of the circle and a tangential acceleration tangent to the circle, there's some actual acceleration between the two, some vector sum of the two accelerations. The nice thing about tangent being perpendicular to the radius or the centripetal acceleration is that they always form a 90-degree angle to each other. So if we know the tangential acceleration and we know the centripetal acceleration, using any of the kinematics, or maybe it's just simply told to us, we can find the total linear acceleration relatively easily by using Pythagorean theorem, that a squared equals b squared plus c squared. Or as you'll often see it written, a is equal to the square root of the centripetal acceleration squared plus the tangential acceleration squared. When dealing with non-uniform circular motion, you have to be a lot more careful because it's a lot easier to make mistakes or to be using the initial velocity when we're at some point later on in traveling and we're no longer traveling at that speed. You're going to want to be able to describe these motions mathematically, graphically, and of course using paragraphs or in words. When we're talking about mathematical descriptions, it's important to know the functions that relate to these types of motion. So first, looking at the kinematics descriptions. These are describing the motion without consideration of the forces that are involved or without consideration of the forces that are causing the different accelerations. We have our standard kinematic equations. In fact, you're already familiar with the first three because those are the big three from when we did one-dimensional and two-dimensional motion already. The important thing to be careful about here, though, is this acceleration is not the centripetal acceleration. Centripetal acceleration doesn't cause you to speed up or slow down. These are tangential accelerations. So when we're describing the change in position or the arc length traveled, that's equal to the initial velocity times time plus 1/2 acceleration tangent to the circle times time squared. If we're talking about uniform circular motion, all of these accelerations are zero. And so we really find out that when we're doing uniform circular motion, it's really only this one that's going to be important to relate arc length or distance traveled, the time and the speed. And then of course the centripetal acceleration, which is v squared over r. This, which is that the v is equal to 2 pi r divided by t. Now, all of those are the important ones for uniform, and of course, as usual, you can see there's a little bit of a relationship here between these two. Now, v is 2 pi r over t, that's the circumference divided by the period, and centripetal acceleration is v squared. Centripetal acceleration will equal v squared, which is 2 pi r over t squared divided by t. See a couple things happen. So you'd end up with 4 pi squared r squared over t squared divided by t. And we see this simple relationship between centripetal acceleration, that centripetal acceleration is equal to 4 pi squared times r squared divided by t. That's a way we can get centripetal acceleration in terms of radius and period without having to worry about calculating the velocity first. Although, if you know the radius and the period, you can get the velocity and then calculate it v squared over r the typical way. When we're talking about non-uniform, then we have to consider those tangential accelerations. Then we use our kinematics equations that we're used to describing them, where we have that tangential acceleration in there, depending on what we know and what we're trying to figure out. We know the 2 pi r over t is still relevant, but it gives us our average velocity, not our average speed, not our instantaneous speed. But we can also get that using the arc length traveled divided by the time, and that relates to our initial and final velocities since it's the average. So that gives us another relationship between the initial and final velocities and the average velocity, which can be useful for some problems. And then of course, the centripetal acceleration, which is v squared over r, which is true for every version of circular motion. to finish up this topic, let's talk about the mechanical descriptions. This is looking at the forces that are causing the motion. Now, this is where these problems can get a little more challenging because there's a lot of different forces that can be at play. The basics of it are really just knowing Newton's second law. We're really going back to Newton's second law, which is that the force is equal to the product of mass and acceleration. Really, that the acceleration is proportional to the force divided by the mass. So what we see here is that the centripetal acceleration, which is the acceleration towards the center, in Newton's second law, force equals mass times acceleration. So in this case, it's the centripetal force equals the mass times centripetal acceleration. Since the centripetal acceleration is v squared over r, mass times v squared over r equals that centripetal force. Now, the centripetal force itself can be the product of a lot of different things taking place. So that centripetal force is really the resultant or the net force along the radius. It's really F net along the radius, not perpendicular because that would be that tangential acceleration, but along the radius. And it can be caused by friction, if it's something like tires on a road with a car that's causing it to turn. It can be tension if it's something tied to a rope or a string. It can be gravity if it's a mass orbiting. We're going to look more at that later on in this topic. It could be a normal force if you're pushed up against a wall on a ride that's going around in a circle. It could be a spring force if you're attached to a spring, or it could be some other force like an electrostatic force or some other force that hasn't been mentioned at the moment. But regardless of what force it is, it's really one of four fundamental forces. You must know the four fundamental forces, although the forces that we really are working on, or that we look at most this year, are the electromagnetic force and the gravitational force. Gravitational force dominates in big structures like us and Earth because it's about mass and it's really large, but the electromagnetic force dominates at small structures like how atoms are held together, how atoms bond with each other, and are actually responsible with you being able to pick up things. So when you're holding something, it's really the repulsion between the atoms in my fingers and the atoms in the pen that are allowing me to form grip. Friction is because the atoms are rubbing against each other, or the way the atoms are interacting with each other. So whether we're talking about tension, gravity, normal force, spring force, all of those, we're really just talking about some version of these four fundamental forces. When we have non-uniform circular motion, there's a tangential acceleration too. Then that's Newton's normal second law. That's Newton's second law as we're used to, which is the net force is equal to the mass times acceleration. In this case, we're going to talk about it as the tangential force, not to be confused with the tension force, but it's the net force perpendicular to the motion, whether that's caused by friction or whether that's caused by gravity or something that's not towards or away from the center of the circle, but actually tangent at that point around the circle. We'll look more at these forces when we're seeing example problems, but it's important to think about Newton's second law and about the sum of forces. We'll look at those forces and we'll describe how forces are related to those motions when we look at some example problems.